Good morning, everyone. Today we're going to start Unit 5, Lesson 3, creating cross-sections by dilation. If you could turn to page 219, we have a warm-up here I'd like you to try. Dilate the triangle BCD using center P and a scale factor of 2. You remember we did this last trimester. If you need a ruler, they're in the boxes over on the counter. You'll need that today. Go ahead and grab those, and we'll give you about 5 minutes on this. Ms. Burfelt, if you would please pause the video and in about 5 minutes play it, and I'll have the answer revealed here for you. All right, let's take a look here. So what I did was I measured the distance from P to B, and I got 25 millimeters. If I'm going to go with a scale factor of 2, I'll take that length from P to B, and I'll double it. So I'll go 25 from center P. I'm going to go 25 and another 25. And that will get me to my new point, which we can call B prime. So that full distance from P to B prime would be 50, 25, and 25. And then I did the same thing for C. P to C was 20, so I went another 20 units out. And that put me at my new spot right here, which we're going to call C prime. And then P to D was 35, so I went 35 and another 35 for a total of 70. And that got me to my final point. And now I can take and do the dilation of triangle BCD. And I'll call that B prime, C prime, D prime. So, look at your drawing. What do you notice? What do you wonder? Right? Think about what you've seen and what this unit is now. Where are we headed? What did we look at yesterday? We looked at three-dimensional solids. Do you see a three-dimensional solid taking shape? If so, can you name it? Now I know you all screamed out as loud as you could, triangular pyramid. Right? If you look at the base, let's consider B prime, C prime, D prime, the base of this triangle, and it grows outward or to the left here, and you can kind of see that three-dimensional shape take place. So if this is a triangular pyramid, you can see we could consider this the base, and it grows outward until it gets to the apex, which is the center of your dilation point P. Now notice the original triangle BCD, that could represent a cross-section of the original triangular pyramid, which is kind of what we studied yesterday. So what are we doing today? Well, we're going to take this idea that dilations can actually be strung together to create three-dimensional solids. So listen very carefully here to what we're going to be doing today. So picture this. A teacher holds a ball or another small object representing point A off the surface of the board and projected directly out in the center of the shape. Imagine the three-dimensional objects created by connecting point A to the vertex of the triangle. A triangular prism and a square pyramid are shown below. So what this is actually, picture a ball coming out right off of the screen at you. If I could, I'd try to make this grow towards you. And this would be like a bird's eye view or the top view down of a triangular pyramid. It's like if you're flying over the pyramids out in Egypt and you look down, this is, when you're exactly over the apex, this is what you would see if it was a triangular base. I believe a lot of the pyramids in Egypt are a rectangular or a square base. I'm not positive on that. But this would be what it would look like from a bird's eye view of a rectangular pyramid. So, how could we dilate each of the two-dimensional figures by a scale factor of 1/2 using A as the center of dilation? Well, what you could do is you could actually take the same idea we did here, measure the distance from each vertex, the apex to the vertex, and then take that distance and cut it in half, and you would get a rough estimation here would be You have to really forgive my drawing here, freehand. We would have an example of a halfway dilation, a triangle that's dilated halfway. And what would that represent? That red shape that I just drew is the cross section. And you could do the same thing here. Find the midpoint or the halfway distance from the apex to the vertex, and you could draw the cross section as a piece. Now, it doesn't just have to be halfway, right? You could do a quarter, you could do 3/4, you could do a 16th. So what you're going to be doing is you're actually going to be creating your own mobile, which is a kind of a sculpture in a sense, which the materials are suspended in air. So listen carefully to what you'll be doing with your group. If you turn to page 219, we have blank paper, which is a thicker cardstock you're going to be using. Rulers, you may use your phone for a calculator if you need it, or use your own calculator. Scissors and string. We have all this material up at the front desk. You're going to work in small groups, and then you're going to piece everything together within your group of 4 to create a sculpture. If you only have 3 people in your group, we'll tell you what to do with that. If you're a group of 2, you could join a different group that might be short a person, or you could just do double the work. It's not that bad. I'll show you. So, your teacher is going to give you sheets of paper. Each student in the group should take 1 sheet of paper and complete the following steps. You're going to locate and mark the center of your paper by drawing diagonals or another method. So think about that. It's going to be a rectangular piece of paper. And then if you lightly draw in the diagonals, that will give you the perfect center. Right? That's probably the quickest way to do it. Please do not fold the paper. I'll share with you why in a little bit. Each student should choose 1 scale factor from the table. On your paper, draw the dilation of the entire sheets of paper using the center as you marked as your center of dilation. So just like I showed you before, here's your center of dilation. You want to take and go either halfway from the apex to the vertex, or you might be 3/4 of the way, you might be 25% or 1/4 of the way. But you're going to dilate your shape. And depending on your scale factor, when you get done with your dilation, you're going to create a new rectangle. So it could look like this, or it might be a big one. And it could look like that. You might even have the smaller one, and it'll look like that. But what you do is you created different cross sections of this potential 3-dimensional model. Then you're going to measure the length and width of your dilated rectangle and calculate the area and record that on the table, which is on your page in your textbook. Then you're going to cut out the dilated rectangle and make a smaller hole in the center. You can just use the compass that we have and poke a hole through it, because you're going to actually thread string right down the middle of it. So all of these directions are on page 219. On page 220 is the table you have to fill out. So each person is going to get a different scale factor. I'll let you all decide who gets what scale factor in your group. If you are a group of 3 people, then 1 person has to do both of these, right? Because this is the easiest one. You'll probably see why very quickly. But here's your scale factor, and then you got to record the length and the width of your scaled rectangle, so that's your new rectangle, and then calculate the area. All right. Once you have that, on page 220, you can read through these directions. It basically says, find a length of string that's more than 30 centimeters. Right? Ms. Burfelt has the string up at her desk, and she has a meter stick, so you can measure out 30 centimeters of string. And then you're going to string all pieces together. But before you do that, you have to make marks on the longest piece of string that are equidistant apart. I'll let you guys kind of read that and decipher it. Then you're going to thread the long piece of string through the hole in the largest rectangle, and you're going to tie a shorter piece of string underneath it so it'll hold the rectangle in place. So you might have to, you get a long piece of string and then you'll get 4 shorter pieces of string. Those 4 shorter pieces are to tie the string beneath it, and that'll hold the rectangle up. And then thread the remaining pieces of string from largest to smallest, tying a short piece of string beneath it to hold up each piece. Then you hold up the end of the string to make your cross sections resemble a pyramid, as your group may have to steady the cross sections for the pyramid to appear. So this is my version of what it will look like. You'll have your 4 rectangles, you'll poke a hole through it, and then when you hold it up by the string, you'll get that pyramid that is created. All right, this is just an example. This is kind of a real life example. See how it isn't perfect? The paper should kind of hold, but you might have to steady it to make it resemble your 3-dimensional pyramid, excuse me. All right, then what we want you to do is just think about what you kind of did, like who had the scale factor of 1? What did you notice? Did you have to do a lot of work for that? And also we want you to think about how the area of the rectangle had changed. Did it change by the scale factor of k, like the length and the width did? Or did the area change by something different? And finally, this is very important, is you should then read through the summary on page 221 and do the practice problems, check your solutions online, and then remember you can work at the Delta Math week 1 when you're done with that. So go ahead and try this. When I come back in class, we can wrap things up verbally and just talk about, and I'm curious to see how your mobiles were created. Good luck, have fun, enjoy, see you tomorrow.